Okay, so we are learning the object detection pipeline, okay? And we have learned the RCNN pipeline, which is the early object detection pipeline. And I think I missed this part. So I think fast RCNN, they are kind of apply this kind of CNN, the early layers of the CNN first, and then they can obtain this kind of 2D feature map. Okay, so in the 2D feature map, the spatial information is retained. So, I mean, these regions, they are encoding the information about the top left regions of the original image, and in the feature maps right bottom positions, they are encoding these regions of the original image. So we can say this is retaining some of the spatial information, and this is because the convolution, 2D convolution operation is operating like this, and they are tending to tending to accumulate some of the contextual information from the nearby pixels. However, they are basically encoding those specific regions. Okay, so yeah, that's the characteristic of the convolution, 2D convolution operation, and that's why we can get the 2D feature map that is retaining the spatial information. And by exploiting this kind of characteristic, what we will apply is this kind of ROI pooling operation, which is a differentiable layer, and we can use this layer inside the deep architecture. Okay, so this is kind of one of the pooling operation, but their purpose is, anyways, using this type of object proposal bounding box. They want to attach this kind of feature regions. Okay, they want to attach some of the feature regions and wanting to map it to some fixed dimensional, one-dimensional vector. Okay, and then we can apply fully connected layers to map it to class and also the refined bounding boxes. Okay, that's what we learned last time. But one important part was missing last class. So, anyways, the fully connected layers. The number of coefficients inside these fully connected layers have to be decided based on the dimension of the previous layer's output. Okay, so for example, if this dimension is 100 dimension, then that FC layer, the first layer of the FC layers, have to be some MLP that maps this one-dimensional, 100-dimensional, one-dimensional vector to some of the one-dimensional vector. Okay, so I mean, these vector have to be in the fixed dimension before mapping it to, before inputting it to the fully connected layers. And actually, these patches, their dimension is varied. The bounding boxes obtained from the selective search algorithm, that actually varies, okay, depending on the object size. So we already seen that their dimension, the bounding box's dimension, is varied, okay. So somehow this cropped feature map, their dimension is varied depending on the bounding boxes obtained from selective search algorithm. But we have to map it to fixed dimensional vector. Okay, so we have to make it into the same dimensional vector to feed forward it to these fully connected layers. So are you guys following this? Maybe yes, okay. So to convert the different dimensional 2D features into the one-dimensional fixed dimensional 1D vector, we apply this kind of ROI tree. And how it works is like this. So this is describing that. So this is arbitrary. This is denoting the whole 2D feature map. Okay, and this black box means this kind of bounding boxes obtained from the selective search algorithm. And actually, inside this black box, we will apply ROI pruning, maybe dividing this bounding box into, for example, 2 by 2 windows, or you can also apply different dimensional pruning operation, maybe it depends on you. But what they will do is, anyways, let's say we are applying 2 by 2 ROI pruning, then inside these bounding boxes obtained from the selective search, we divide it into 2 by 2 regions, and then apply max pruning for each window to get 1 pixel from each window. Then maybe we can get 4-dimensional vector. Okay. So regardless of the original bounding box size, because we are dividing it into the fixed, dimensional sub windows. So, and we will pick just one value from those sub windows, so we can get the fixed dimensional vector. Okay, so that is exactly what I mentioned here. Okay, so from the varied sized windows, we will divide the inner sub windows. Okay, and then we will pick a fixed dimensional value from the each sub windows. So that's how we will get the fixed dimensional vector from the varied windows. Okay, and then we can apply the F layers whose number of coefficients are fixed. Okay, are you guys following this? Yeah. So, and then we can apply the two losses that I mentioned, the cross-entropy loss for the classification, and locational loss, which is composed of smoothed error loss that is combined with L2 and this kind of error loss. Okay? But this detail is not that important. You can just roughly think this is the same as the mean square error loss we already learned. Okay. Anyways, this is how fast RCNN is working. Okay. And faster RCNN, as I already mentioned, there's some heuristics remain in the object proposal generation part. It requires the clustering algorithm, which is not that optimal, and also requires many iterations to get the clusters. So there was bottlenecks remained in this kind of algorithm. So fast RCNN, they are solving this kind of bottleneck inherent in the fast RCNN algorithm, and improve the speed, at the same time improve the accuracy. So this is the comparison between these three algorithms, RCNN, fast RCNN, and fast RCNN. So the time is becoming reduced. At the same time, the accuracy is becoming robust. Okay. So now, this is the summary for the object detection pipeline, which is, this is one of the most famous object detection pipeline, but as I told you before in previous class, this is the two-stage algorithm. Basically, they operated in the two stages. First stage, they wanting to localize the object region, and in the second, they want to classify those regions into semantic classes. Okay, but we will also learn about some of the one-stage algorithm. YOLO, maybe most of you are already familiar with this. YOLO is one representative algorithm for one-stage object detection pipeline. And actually, it has many versions. So, but we will learn about the earlier versions of the YOLO. Maybe after a few classes, we will learn about this YOLO. And also, from now on, we will learn about some object detection pipeline based on the transformer algorithm. Okay. So transformer actually is very popular these days. So you already know about the GPT. And GPT is abbreviation for pre-trained transformer. Okay. So GPT comes from generative pre-trained transformer. Okay. So GPT is using the transformer, and this transformer is actually coming from the natural language processing domain, but nowadays it is proven effective for the computer vision domain as well. And it is actually replacing the CNN algorithms. Okay, so CNN, as I told you, from 2012, from the AlexNet, it was proven effective by recording the state-of-the-art performance in image classification tasks. And after that, ResNet, there are several famous algorithms such as Vision&Learning, Google LUNet, and ResNet. Okay? And year of 2016, ResNet comes out, and thanks to the residual component, it performs even better than the human performance in some of the tasks already. But transformer is nowadays replacing this kind of CNN-based algorithm. And I will tell you about how this transformer is, beating the CNN algorithms in object detection tasks. Okay. And before that, I will introduce you some of the, history for this transformer algorithm. So actually transformer, and also I will tell you about some of the NLP domains history first, because this transformer is coming from the NLP domain. So this kind of explanation is necessary, actually. So you have to know about the RNN first, RNN first, okay? So NLP, it is basically dealing with some of the text signals, right? This is, text is composed of the several words, right? Okay, and for example, I am a student, okay? This kind of sentence is the text signal, and they are composed of several words in it, okay? So basically, in the NLP domain, the input and output signals are sequential data, okay? So when dealing with this kind of sequential data, this kind of RNN algorithm is efficient, okay? So you have to first understand this kind of RNN structure, okay? So this is the input, denoting the input, and this is denoting the output. And this is the, layers inside the network. So, without this recurrent part, this is same as NLP layer. So, this is some layer, and this is output, okay? I'm redrawing it without this recurrent component. So, this is actually same as NLP, multi-layer perceptual, or linear layers we already learned. Okay? Are you guys agree with this? Maybe, right? Okay. But MLP can only deal with one-dimensional signal, okay? So MLP can deal with one-dimensional signal, one-dimensional vector. They multiply some weight and add some bias to get the output. Okay, that's how MLP is working. But how to extend this MLP to deal with some of the sequential data? Maybe the computer vision, the MLP researchers are, proposing this RNN to consider to expand the MLP for the sequential data. So basically, in this RNN, this is the recurrent component, but if we flatten it, it would look like this. So the basic blocks, they are same as the MLP that I drew already. Okay, given X, it output each outputs for that specific input by multiplying some weight and adding some bias. Okay, within this hidden layer. Okay, that's when given one time input, okay, that's same as previous MLP. But the difference is, let's say there are two sequential, there are two sequential data having two time, okay, two time sequence, then independently apply these MLP layers to output for this independent input sequence might be suboptimal. Let's say if this is some sentence describing this kind of thing, I am, then let's say think about translating this English sentence to some of the French language. I don't know about this French, but anyways, there's some French word for I here and some French word for this M here, okay? When translating this sentence, I am, sometimes we have to consider the previous, their, their mutual context, okay? So when translate I, maybe we can use only I, but when translating this M, we have to maybe consider what was the previous word to this, okay? And that can be reflected in this route, okay? And also, also we can think about this kind of thing. So let's say I am a student here. Okay. So when translating this I am a student to some of the French words, okay, then for when translating I, we can translate it seeing only that. But for the second, translating the second word, we can anyways consider the previous word, okay, and that information is actually coming from this route and can reflect that to translate the second word. And also we can transmit the previous word information when translating the third word, okay. Anyways, this kind of how to say route to transmit previous information to subsequent when achieving the subsequent tasks is helpful when dealing with this kind of sequential data. Okay, and actually, when to represent this kind of architecture, I have to say, simply we can draw it like this, having some recurrent route. Okay, so we can just draw the RNN, the recurrent neural network, this way. But one important problem, when making this recurrent neural network, there's vanishing gradient problem appears. So we already learned about this vanishing gradient effect when we learned about resonance. Okay? Within the CNN, when we stack more than maybe 20 layers, 20 CNN layers, the deep architectures are tending to produce better accuracy when the overall architecture is getting deeper. But if we stack more than 20 layers, it is getting actually less again. And that was because of this vanishing gradient effect. The gradient, their scales is becoming small when stacked more than 20 layers because of the precision issue. And we actually use the residual connection to bypass such problem. So if you miss this part, then please watch the previous video. Anyways, the same issue is valid here. If we stack sentences, if we use the sentence input, which is very long, then when transmitting these signals, if maybe the length of the sentence is very long, then their gradient is becoming close to zero, and they simply represent it as the zero, and the training will not be happen correctly. Okay, so then actually we can call that phenomenon as the vanishing gradient phenomenon. Okay, so in RNN, this kind of problem is severe. So vanishing gradient. So the NLP researchers are thinking about improved version of the RNN. Okay, and that is actually the LSTM I will explain from now on. Okay, and also in RNN, it is non-trivial to parallelize because we do not know for each data, their length is not fixed. Okay, so the number of these hidden state is varied for each sample. So it is sometimes not that trivial to apply the parallelized algorithm, such as the batch-wise operation when dealing with this RNN. Okay. So that's the weakness in the RNN. Okay, so and LSTM, that whose name is long-term short memory, it is the improved version of the RNN. So it actually tackles the vanishing gradient phenomenon of the RNN, and it indeed works. So nowadays people are using this LSTM instead of the RNN. Okay, and it has several input and output. So there are two important things here. This is called as cell, and this is called as hidden state. But we regard this as actually the output. Okay, and this is we regard that as some of the contextual information. Transmitted from the previous layer. Okay, and this is the input for that time step. Okay. This is actually here, YT is the output, but actually they are almost same. Okay. So here you have to first, we will first infer some of the intermediate output by combining some of the input first. Okay, so these two inputs are coming from the previous time steps output. So this CT minus 1 is denoting that previous layers, previous time steps, cell state. And here HT minus 1, that is representing previous layers output or hidden state. And X dot T, that is meaning current input. Okay. So using some information coming from the previous time step combined with current time steps input, we first generate some of the intermediate information. So this app is called as forget bit. So this controls how much information we will forget for this cell state. Okay, so we will first combine the hidden state from the previous time step with the current time steps input and apply some of the linear operation, okay, and apply the nonlinear layer, and then get this forget bit. Okay, and this forget bit controls how much information we will lose for this cell state, previous layers cell state. Okay, and also this we will also infer some I bit, which is the information bit. Okay, so using the same concatenated signal, hidden state from previous layer and correct input, we will apply the linear operation again and nonlinear operation to get this information bit. Okay, and also we will also get this cell state, temporary cell state for current. This is actually denoting T's current cell state. Okay, you can think this as C of T. So we only have CT minus 1 now, but we will first generate some of the current cell state from the same input. Okay, by combining these two information, we will first generate the cell state. Okay. But we will not use this C tilde directly, but by combining it with previous cell state multiplied by forget bit, okay? And also we will use the cell state of the current step multiplied with the information bit, okay? And then we will somehow weight summing previous cell state with the current cell state to generate indeed current state cell state. Okay, that is actually represented here. Okay, so forget bit is multiplied with previous cell state, and so this is intermediate output for information bit and current time step cell state, and they are multiplied and added to this with this previous information. Okay, so this becomes the current time steps cell state. So here, the important motivation of this LSTM is they are actually controlling how much information we will use from the current cell state. At the same time, how much information we will lose from the previous cell state. Okay? And this is actually reducing the vanishing gradient problem. Okay, we can actively control the contribution of previous and current time steps information, and that actually leads to reducing the vanishing gradient. Okay, and also for the output, we can also generate the output here. Okay, first output bit first here, and using the current status cell state combined with input output bit, we will infer the final output for current timestamp. Okay, and we will transmit to the next cell. At the same time, we will regard this as our output. Okay, that is the LSTM. So forget bit. Sometimes they call this as the gate. So forget gate. This is F. Input, not information bit. This is the input bit. There is I bit and output gate that is denoted as O. Okay. So I mean this kind of intermediate gate, they are controlling how much information we will retain or use or forget from the previous input and current input. Okay. So that is actually controlled by each component. So they are becoming robust for Banach gradient effect. Okay. So that's the explanation for the LS10. So nowadays, people are using LS10 when they use the RNN. Okay. And I have to explain this kind of sequence to sequence things to you, maybe. Using these LS10s as the basic block, what is achieved when doing the translation is actually this. Our input is this kind of sentence, and this is the output, maybe French. Okay. Using this sequence to S2S, or sometimes this is the abbreviation for this sequence to sequence network. And we input some of the sentence and wanting to translate it using this sequence to sequence network. Okay. And if you magnify this sequence to sequence network, then it looks like this. This is actually overall sequence to sequence network. And they are actually composed of the encoder and the decoder part. Okay. So actually, we already saw this encoding and decoding process when doing the segmentation or image inpainting task before, and maybe you are familiar with that. Actually, what encoder does is they are wanting to generate some of the feature from the input signals, okay? And what decoder wanting to achieve is using this feature, they actually wanting to make the final output, okay? That's what decoder is doing. And I will explain how this kind of algorithm works now, okay? Encoder, we want to generate some of the feature, okay, from the overall, say, input, okay, input sequence, okay. I is first coming to the first LSTM, okay, and then it transmits some of the vector that encodes the features for the I word and combine it with N, and then again transmit the first two words information to subsequent LSTM. And here they also encode three-word feature by combining this A feature with previous layers feature. Okay, and also we get the final word and make it into the feature vector. Okay, that's how this encoder is working. Okay. And decoder, what they do is, this is important actually. When translating the first word, I mean, this SOS is the, how to say, the keyword, or you can, not keyword, some of the token, you can regard this as the token. And this SOS is the starting token. Okay, this is the starting token, and EOS is the maybe ending token. Okay. So after encoding the feature, getting the overall sentences, input sentences, you will input this starting token to the LSTM of the decoder. Okay. Then at the first time, you don't have any how to say output from this decoder. So at first time, you will just input this SOS to the decoder, and then that decoder will output the first word of this French sentence. Okay, it only output this first. Okay, and in the next step, sorry. In the next step, you will input these two words. You are getting this first word from the decoder, right? In previous step, so you are inputting this previous times output as the input now, and then you will get now these two output. Okay, so this is the new word. Okay, and in the next step, you will also use this word, two word coming from the previous time steps output as the input to this decoder, and combined with this feature vector, you will infer the third word. Okay, and this happens until you get the ending token. Okay, so are you guys following this? Okay, so I mean, decoder is similar to CNN operation, but you have to understand this decoder. We call this as the auto-regressive, we call this as the auto-regressive way because we are using the predicted output as the input to subsequent prediction. Okay, that kind of thing is called as auto-regressive method. Okay, you have to understand this. Okay, and also decoder, encoder is working somehow with the one feed forward. Okay, encoder is once executed, but decoder that is multiple times executed. Okay, that's the characteristic here, sequence to sequence model. Okay, and transformer that is actually proposed to replace this kind of operation. Okay. Oh, I cannot delete that. So the encoder-decoder architecture, that's works similarly here. Okay, their overall architecture is similar to previous sequence-to-sequence network composed of the LSTMs. Okay, but inside this encoder and inside this decoder, their main operation is different from LSTM. Okay, so as I told you, when getting output here, you have to calculate this first, okay? And when calculating this, you have to get this intermediate output first, okay? Somehow this encoder and also the decoder, they are both works in the sequential manner, okay? To get the subsequent output, you have to calculate the previous output. Okay, that's the how sequence to sequence model composed of the LSTM works. But here, in the transformer architecture, when getting this feature, they are actually apply operation called as attention mechanism instead of this kind of sequential operation. And what this attention mechanism denote is when inputting this sentence, I will now skip this part, embedding part. Okay? You don't have to care that now. This forward, but when inputting this forward, we first, of course, transform them into the feature for each word. And in the NLP domain, there's some method that can transform this kind of word to fixed dimensional feature. Okay, and actually, here we get those kind of feature, of course. And what attention mechanism does is it actually densely perform the dot product operation for this input, okay, to get this feature, okay. So I mean the objective of this encoder is getting the feature vector from the input signal, right? In the sequence-to-sequence model, it sequentially calculates this feature, okay? But in the transformer architecture, in their encoder, they apply attention mechanism to calculate this feature from the input signal, okay? And that attention mechanism actually performed as this kind of dot producting between this input word. Okay, I will explain that using the say using some of the formula in the subsequently. Okay, but at this time you can roughly can understand this is some dense producting between the input. Okay, the attention looks like that. And also, but I mean, in the decoder, it actually works. I mean, how to get the final operation, that is also composed of the attention mechanism. However, for getting this output, it also sequentially works. I will show that. So, I mean, decoder, it also works in the auto-regressive manner. Okay, so when interpreting the first output, this, when after, I mean, after getting this feature from the input signal, you only apply this starting token to get this first word in French. Okay, but I mean, inside this decoder of the transformer, they calculate it as the attention operation. But previously here, it was the LSTM, and we are applying some of the linear operation. But here, we are applying attention mechanism to combine the feature of the input signal and the starting token, okay, to get this. But it actually anyways works in the sequential manner for interpreting each output. And after getting this first output, you input it here, and it starts the second phase. Okay, so given this starting token and the first word translated, you combine their feature with the input feature using the attention mechanism to output the second word. Okay, and again after that, you regard this as the input, next input, and I mean encode that as the feature and apply attention mechanism between these three input and the feature, okay, from the encoder, and get the third output. Okay, it happens until we get the ending token. Okay, so are you guys following this? Maybe yes. Okay, this is very important thing. Okay. 다 이해되나요, 이거? 이해 안 되는 분 손 한번. 다 되시죠? 이거 되게 중요합니다. 트랜스포머 많이 쓰이고 요새 어쨌든. So one important thing is, anyways, the core operations of the encoder and decoder that is replaced to the attention mechanism. Okay, but the overall operation, I mean, such as this autoregressive operation in decoder, they are retained. Okay, but one important thing we have to note is the encoders of the this transformer, they cannot actually express the orders in input. Okay. So, I mean, we are having this kind of sequence data. So I is before the M word, and IM is before this A. Student, I mean, this IMO is before this student, okay? But I mean, when implementing, this is very subtle thing. I mean, when implementing this encoder operation using the attention mechanism, there is some order here, right? It seems like that there's some order here, but in actual implementation of the attention mechanism, there is actually no order, okay? They are actually just calculating the dense dot producting between the input, and there is actually no order. But humans are, I mean, perceiving this sentence as having some orders between words, okay? But in the encoder of the transformer, we cannot explicitly represent the orders of the world. Okay? So because of that, we are actually have to encode the positions of the each input. Okay? That's called as the positional encoding. Positional encoding looks like this. So it has some encodings like this. So I is the first word. Okay? Their position is activated in the first leftmost side, and M is the second word. So this is activated. So their log position is activated in the positional encoding. Okay. So actually they are summed to the original word vector and then inputted into the encoder. And also in the decoder, this kind of same positional encoding is used. Okay. So because the attention mechanism, it is kind of the parallelized operation, and it cannot actually decode and encode some of the spatial information inherent in the sequential data input. Okay. So we have to embed this kind of positional encoding in the transformer's input. Okay. So this is the encoder and this is the decoder part. Okay. So this is the transformer that I understand, but thing is, actually this is the first paper that proposed to use the transformer in the NLP domain. I think the paper is worth reading, okay? But they represent the transformers with this figure. So, I mean, actually you have to understand that this figure is same as this figure. Okay. I mean, the left part is denoting the encoder part, and the right part is denoting the decoder part. Okay. I will explain why those two figures are same. So this is the input, okay, which is the sentence, and we have to apply the positional encoding to each word in the sentence, okay. And actually, here the words themselves are represented as the feature, okay? And actually they are feed into this kind of multi-head attention layer, okay? This is actually the attention mechanism that I mentioned, okay? And actually, the attention mechanism, as I mentioned before, they are represented as this, okay? I mean, sorry. We first, this is the input feature, and here we are transforming each input into key query values. Okay, we just call this as the key query value. There are no specific meaning. K, Q, V. The first input is called as key. This is called as Q. The third one is called as V. And when you see their formula of the attention mechanism, you can feel like that actually, I mean, KQ is dot predicted, and they applied with some softmax later, and dot predicted again with V. So that's how this attention mechanism works, and they are actually represented as this kind of thing. So, given word vector, they are their key values are densely producted with their query values. Okay, so I mean that kind of relation could be represented as this dense producting. I will re-explain this later. Anyways, they are applied with this attention mechanism, and their input is applied with some of the feed-forward network, which is actually the MLP layer, multiplying some weight and adding some bias, and then output it. So here we will get some of the feature that encode the input sentence, okay? So that actually coincides with this figure. So we are getting some sentence input and apply some positional encoding and apply dense producting between input and get this feature map, okay? But before that, we apply some of the MLP layer here, right? Anyways, this represents the encoder part, okay? And then I will explain the decoder part, okay? Sorry. So here is the output, okay? I mean, this is denoting that at the first step, they will have only the starting token, but after that, they are showing actually this shifted right is actually meaning that their previous layer's output is auto-regressively inputted as the input to the decoder. Okay? As I mentioned here, first, the starting token was inputted to the decoder, okay? But at the next round, first time steps output is also inputted to the decoder, okay? So that is actually meaning the shifted right here, okay? And anyways, they encode this shifted right output and apply some positional encoding and transform it to key query values of the attention mechanism, and first get some output feature for this output signal, okay? And the next thing is very important. This is also the attention mechanism, okay? But you have to note their inputs are a little bit different from previous ones. So two of the three input to the attention mechanism, those are coming from the encoder feature vector, and one input to this attention is coming from the earlier layers of the decoder. And then they apply attention mechanism for these three vectors, okay? And then generate some output. So some of the information contained in the feature vector, which is coming from the encoder, that is combined with some of the output, some of the input to the decoder, they are combined in this attention mechanism, okay? And then they apply some of the feed-forward layer subsequently and map it to the output, okay? That is the decoder layer, and you have to feel that that is actually same as this part, okay? So if we input this, then first self-attention is applied to encode this using the self-attention, and then here another attention is combining these two information, and some MLP layers are applied and estimate this, okay? So this coincides with what I explained here, okay? So that's why these two figures are actually describing the same thing, okay? And another important thing you have to understand is here, these two attention, we will call that as the self-attention. This is called as the self-attention because all of the key query values, those are coming from the same signal, okay? As you see in these arrows, those three key query values, those are coming from the same signal. So that's why we call that as the self-attention. But here, this attention is actually combining these two heterogeneous information, and two inputs are coming from one source, and the other source is constituting the other input to this attention. So we call this attention as the cross attention. Okay, but their attention mechanism is basically same, but their input sources are differently constituted here. Okay, and also sorry. Here you can also see there's a mask. This kind of masked word here. When implementing this decoder, we will not actually implement this as I mentioned here. So here I mentioned that it works in the autoregressive way. Okay, and when getting first output, we input it as another input to the decoder and get another output here. Okay, I explained that as if it works in the sequential way, but indeed what it works is for first input we mask how to say I am a student, and there's I am a student. Sorry, this is not I am a student. Starting token and first word, first French word, that was JE, maybe JE, Swiss student. So for the I, when applying attention mechanism, these values are not visible. It only cross-attended with this SOS, okay? And when getting the second output here, this M and I, those two are applied with self-attention. So now this and this are, I mean, applied with attention with this AM, but these are not shown, I mean, because of the operation of this decoder, okay? So we have to apply some of the masks in this invisible input of the decoder. And when getting, inputting these 3 words, we also have this, okay? And we apply mask here, and A is self-attended with these 3 output word, okay? And when inputting this 4 word, we don't use any masks, okay? I mean, this kind of sequential autoaggressive operation can be implemented by applying this kind of masks for the input. Okay, so because of that, during the training, we apply this kind of masked attention instead of sequentially operating these decoders. Okay, so you can see this kind of masked things in the overall pipeline. Okay. So anyways, you have to understand this figure is same as this figure, okay? And you have to roughly understand how transformer is working. And maybe next Monday, I will further explain about the detailed operation of the attention using this kind of figure, okay? And also I will also explain what would be the multi-head attention. And also I will explain, this DTR is the transformer-based object detector, okay? So now the input to the transformer encoder-decoder structure is similar, but now our input is image instead of the sentence, and our positional encoding is now 2D, okay? And applying the 2D encoder and decoder structure of the transformer, we output the object and their locations. Okay, that's the DTR architecture. So I will explain how we can extend this DTR, towards the image domain. Okay. Okay. So let's finish here for today's class and see you next Monday. Thank you.